let us try to remind ourselves a little bit of where we were last time. Do you remember that we were discussing these signals which have a spiral structure or a spiral geometry? Remember that? So, 1, then 1 at an angle of omega, this is happening in complex numbers, 1 at an angle of omega, 1 at an angle of 2 omega, 1 at an angle of 3 omega. On the other side, you would have 1 at an angle of minus omega, 1 at an angle of minus 2 omega, 1 at an angle of minus 3 omega, right? If I were to show it to you on complex planes, then it will be something like this. So, 1 will be here, 1 at an angle of omega here. By the way, please get used to the fact that I will put the real axis like this from now on, okay? It's just visualization, right? Nothing different is happening. I'm choosing to visualize it that way. Why? Because, I mean, we are learning signal processing and we want signals to look like graphs, don't we? So, we want the real axis to look vertical. That's the only reason, okay? So, this is fine, right? So, 1 at an angle omega, 1 at an angle 2 omega, 1 at an angle 3 omega, 1 at an angle minus omega, 1 at an angle minus 2 omega, 1 at an angle minus 3 omega, okay? Is this okay? So, if I were to draw all of this together, like for example, if you were looking at all of this, this stack of complex planes from this side, what will it look like? Can you draw it in your mind? Yeah. So, this will be 1 and then this will be 1 at an angle omega, this will be 1 at an angle 2 omega. Okay, by the way, this is my real axis, this is my imaginary axis, just my convention. 1 at an angle minus omega, minus 2 omega, okay? And so, as this axis progresses, I am going to call it time axis, but you can use signal processing in non-time domains as well. Just most of the times you are doing signal processing with time. So, I will call this the time axis. As time progresses, this is the direction in which your spiral signal is progressing. Okay, these are the spirals. Now, what are the parameters that will define a spiral? Periodicity as in?
At what intervals is it rotating? It's changing.
So where do you see it in here?
Length between two. Yes, length between two angles for rotation. In 1 minus 1.
How much is it? Omega. Yes. Okay. So one parameter is omega itself. How much are you rotating by in the duration of one sample? Okay. And so it would be okay to call omega angular speed, right? The speed of rotation. Except that angular speed you will usually have it in angles per unit time. This will be in angles per sample, at least when we are doing discrete signal processing. If you are doing continuous time signal processing, then you will have to have a time unit and you will have to have measure omega in angles per unit time. Okay? So this is omega, so this is omega angle per sample, correct? What happens if I increase omega? It will go faster, right? Think of it as the time axis, then what is happening is going faster. If omega is fast, omega is more, then it's jumping more per sample. So it is moving faster. If your omega is really small, then it is moving only that much per sample. Okay? What are the other parameters that can change and I will still call it a spiral? Time between rotation? What do you mean?
So if the planes you have drawn are much farther apart.
That's an appropriate point actually. So the distance of these points could change is what he is pointing out, and that is correct, and that is called a sampling frequency. How close or far apart are your samples in a time? But right now we are assuming we are already in the discrete time domain. So whatever is that has already happened.
I don't know. In continuous it won't matter but in discrete it will actually matter more, right?
You're right. You're absolutely right. So in discrete, it is important to know when you have sampled. It is important to know what is the actual time distance between two samples. But for most of the theory, it doesn't matter. It actually only matters while converting from continuous to discrete form and then converting back from discrete to continuous form. The rest of the theory is mostly done without reference to the sampling rate itself.
It seems like in practice this should matter a lot, right? How frequently you are sampling. Like maybe in theoretical equations it may not show, but while actually working with signals.
Absolutely it will, yeah. And there will be a part of some lecture in the future where I explicitly talk about sampling rate and what that means and so forth. Okay? To put what I said in other words, mathematically this is a discrete spiral, and the shape of the discrete spiral doesn't change by changing the sampling frequency, because the discrete spiral is already just a sequence of complex numbers. The information of what is the physical time distance between those complex numbers is not in this data structure, is not in this mathematical structure. It is stored elsewhere. Okay? So, okay. What other parameters are there that I could change and it will still be a spiral? The length of the vectors. Okay. So, for example, this could be 2, right? So, 2, and then this will have to be 2 angle omega and 2 angle 2 omega and so forth. Okay? That will still be a spiral. It will be a larger spiral. Okay? Correct? What else? What else could you change and it will still be a spiral? So we saw two things, omega, okay, and this, the length of this. What else could change?
If it went in the other direction.
If it went in the other direction. That's a good point. He's saying it's just changing omega. In what way? Use a negative omega. Okay, so that's nice, and that's a convention. By convention, we'll say that positive omegas are moving counterclockwise and negative omegas are moving clockwise. Okay, and so yes, whether it's a right-handed screw or a left-handed screw is an important distinction and correct question. But we will index both of them using just different values of omega. Is that okay? By the way, this brings me to an interesting point. This omega, which is the angular speed, is also called the angular frequency. Angular frequency or just the frequency. Okay. Have you heard of the term frequency before? I'll try to explain where that terminology comes from. For a moment, think of continuous time instead of discrete time. Okay. Then what would be the units in which you will measure omega? I just said this a little while ago. It will be? Like some time unit as in be more specific. It will be in? So it will be in angle per unit time. Radians per second is one unit that could be used. Okay. Or it could be turns per second. Correct. So this turns per second thing, what does it mean? Let's say 20 turns per second. What does it mean? What is 20 turns per second? It is a spiral that is making 20 turns in 1 second, right? Like a neutron star going around 20 times a second. Okay? Neutron.
Change in one angle, meaning like from going from 1 to 1 omega is a turn, or the entire thing, complete 360 is a turn?
360 is a turn, always. One turn. Turn is just a different unit of angle, right? As we saw in one previous lecture, turn equals 2 pi radians equals 360 degrees. Okay? So, if something is making 20 turns a second, right, that is, you can call it angular speed, or you can call it angular frequency, or you can call it frequency when put in terms of turns per second rather than in terms of radians per second. It becomes more obvious to see why it is called frequency. Basically, what do you mean by frequency? Frequency is answering the question of how frequently does something happen. In 20 turns per second, what is happening 20 times a second? Yeah, it's making a complete turn. Or another way to think of it, it's pointing in a specific direction. Let's say pointing forward 20 times a second, right? So that is the frequency. That's where the term frequency comes from. Okay? This, by the way, also makes it, this picture makes it obvious why you have the concept of positive frequency and negative frequency. When you think of, like if I say 20 times a second, what's another name for times a second, by the way? Hertz. 20 hertz, right? If I say 20 hertz, that something happens 20 times a second. If I say minus 20 hertz, something happens minus 20 times a second. Doesn't seem to make sense, right? And if you have done some Fourier transform theory before, you might have been confused by why are there negative frequencies in the first place. But what is minus 20 hertz? Yeah, minus 20 turns, it's just 20 turns in the clockwise direction. Okay? Not that confusing when you think about it from this geometry's point of view. Okay? And last time, if you remember, we'll get back to it, but last time, if you remember, you would remember that we need both that positive spiral and its anti-rotation spiral to produce a real signal. Right? So its usefulness only occurs when the spirals work together. Its usefulness to real world, to real numbers, occurs only when we use these two spirals together. And that's why we need both the plus 20 and the minus 20 turns a second. Question? Any question, anyone? Is okay? One more thing can change, but so omega can change. Yes. The size can change. What else could change?
I'm not sure how, but I think if we change the dimensions of the vector,
Dimensions of the vector. Okay. There are higher dimensional variants of this, but let's not go there. See, I mean, yeah. I hope the point here is clear that we are using these two-dimensional objects, the complex numbers, because they are useful to describe things which are important to us, which are actually just one-dimensional objects, which are real numbers. And the complex numbers just as a mathematical game gives us a rich set of eigenvectors. We'll come back to that in a minute. Right? A very nice set of eigenvectors to play with. And that's why that's the game that is why we are using this higher dimension. We really have no reason to do it in further higher dimensions. Though we could ask ourselves the question of what happens if I do 3D and 4D objects as samples. It's not that useful to us for our purpose. One thing, okay. Now, coming back to this. One other thing that could change is the following. How about, suppose this was not 1, but it was 1 angle 30 degrees. Is that okay? Is that okay? So, and then what will this have to be? 1 angle 60 degrees? 30 degrees plus omega. Right? Because it's still a spiral whose frequency is omega. Okay? But it started at a different angle. Okay? So, imagine your original spiral and the whole spiral has now moved by 30 degrees. That is what has happened. Still a spiral, but the whole thing has moved. Okay? So, it is traditional to call this phase. Okay? It's traditional to call this amplitude. And it's traditional to call omega what? Angular frequency, just frequency. Okay? So, phase, amplitude and frequency are the three things that can change to produce various of these spiral shapes. Is omega and phase the same? Why not?
It's a constant. Yeah.
So, once again, this 1 angle 30 degrees, but omega, but your frequency is still omega, then your next sample is 1 angle 30 degrees plus omega. And the next sample after that is 1 angle 30 degrees plus 2 omega. And the next sample after that is 1 angle 30 degrees plus 3 omega. Okay? Phase is 0, correct. 1 is 1 angle 0. So the phase here is 0. Is it clear now? Question? What is the value here? One angle 30 degrees minus omega. One angle 30 degrees minus omega. Okay, and my one angle 30 degrees minus 2 omega, one angle 30 degrees minus 3 omega. Is the distinction clear now? Huh? Phase just decides like your initial angle, your starting angle, which could be anything. Okay? And omega is the speed at which you are rotating. Correct? Where did you start and how fast are you rotating are two different things. Okay? Both of them are parameters of the spiral. Now, when you are doing this in complex numbers, the amplitude and the phase can actually be represented as a single complex number. Okay? And sometimes you will call this the complex amplitude. Correct? As I mean, it's basically just the value at zero sample. The value of the spiral at the zero indexed sample is the complex number whose argument is the amplitude and whose magnitude is the amplitude and argument is the phase. Does it make sense? Okay. So sometimes together you will call this complex amplitude. And if that gives you nightmares of quantum physics, I think quantum physics is actually using this theory, but they are saying it in extremely different form. Okay, but forget quantum physics. So we are doing this for like normal things. Yes.
What's the point of using a phase?
What's the point of using having a phase? So question is, what is the point of having a phase? Let's try to recollect what was the main important theorem that we studied the last time. What did we study the last time? That any such spiral is an eigenvector of any convolution. Remember this? Right? So, why does that happen? That happens because, let us say that, you are, let us say you have some convolution and that is going to produce some output. Okay? So, these weights are going to multiply these values. Which values do I have? Minus 2 omega, minus omega, 0 and omega. Okay. Are going to multiply these values by some numbers and that will produce some sort of a output. Okay? If I do the same thing at the next location, what has happened is that your entire spiral has stepped forward by omega, and so this whole diagram gets rotated by omega, correct? And so your output gets here. Okay? Now, if you look at this output is also a spiral that is rotating at omega, correct? The output of the convolution. Correct? I am talking about a spiral going through a convolution process. And the convolution has specific weights on it. Okay. So, this output of the convolution is also rotating at the same angular speed omega, Yes. What is different? Amplitude is different, possibly. What else is different? Phase is also different. That's what makes phase important. Okay? Because convolutions can change both amplitudes and phases of spirals. Is okay? But what can they not change? Frequency. Omega cannot change. Is this okay? You put in a spiral of a particular omega, you are going to get out a spiral of the same omega, same frequency. But it could be at a different amplitude and different phase. Okay? Yes.
So, what is an example of a phase changing convolution? Like what will the numbers on the display?
What is an example of a phase changing convolution? Yeah, sure. So let's say you have a convolution that is 1 and 1. Okay? 1 times the current sample, 1 times the previous sample. Okay? No, so now we have to calculate it. This is 1. This is 1 at an angle minus omega, correct? That together will produce an output. Yes? And what will be the amplitude and phase of this output? Calculate.
Intermediate angle between these.
The angle is easy to calculate. Calculate the angle at least.
Minus omega by 2.
Minus omega by 2. And what is the amplitude? What? Root 2? It's not root 2. Omega is not 90 degrees. It is root 2 only if omega is 90 degrees. What are you doing? Huh? Cos omega plus sin omega? Something, yeah, I like that. Something like that. I think it is 1 plus cos omega. Yeah? 1 plus cos omega? Sounds very nice to me. Which is probably something else as well. 2 cos omega by 2. 2 cos omega by 2 is very nice. Is 1 plus cos omega the same as 2 cos omega by 2? 2 cos square. Yeah, I don't like that.
2 sin square omega by 2.
2 sin square omega by 2 is 1 minus cos square omega by 2, which is... Anyway.
It is basically a vector, this thing, right?
Yeah. Yeah, it is, yes. So, you have this 1, let's do it. You have this at an angle omega, right? Oh, sorry, 1 at an angle minus omega. Okay, 1 at an angle minus omega. Okay. And you have to calculate the length of this thing. Okay? Length of this thing. And the length of this thing, correct? Which is the resultant of these two. And the length of this thing, if I drop a perpendicular here, this is omega by 2. This is 1. So this is cos omega by 2. And this is double that. So it is 2 cos omega by 2. I like that. 2 cos omega by 2. Do you like that now? 2 cos omega, which is not 1 plus cos omega, by the way. But it is something. No, it is something else as well, right? Like some trigonometric thing happens to this if you want it to know. Anyway, we don't have to worry about it. That's not the point. The point is to show you that there exists a convolution that changes the phase angle. Yes?
You could have just shown a rightward shift.
Sorry?
Just a rightward shift of one and one would also change the phase angle. Like instead of taking the one down, if you just took the one that's going rightward, that would also change the phase angle, right?
Yes, just the rightward shift would also change the phase angle. If it was just this as a convolution, yes, what would be the phase angle then? Just minus omega. Okay? Rotation will be?
Omega, right? Because that doesn't change.
Rotation as in rotation speed will be omega. Yes, that doesn't change. Okay. So, actually, now that we are on this, let's analyze this further so that I can make the point I was making the last time better. What is this spiral? What is the frequency of this spiral? Omega, correct? Frequency of omega. Let's take another spiral whose frequency is minus omega. Is that okay? What will this diagram look like? Same convolution, I am analyzing the same convolution with respect to different spirals. What does this diagram look like? Now this is one, what is this? One angle omega. You understand this, right? Why is this minus omega for omega and omega for minus omega? Correct, because we are going reverse in time. And why are we going reverse in time? Because we are using the gather rule. So f of 1 attaches to signal of minus 1. Okay? So 1, 1. What is the amplitude here? Two cos omega by 2 at an angle of omega by 2. Okay? This is very intriguing. If I were to draw this similar diagram here, you have this and this. Okay? The spiral is now rotating this way. This spiral is rotating this way. This spiral is rotating this way. And your output is like this. Okay? Correct? Now, try to understand this. Okay, let me ask you a question and see if you can answer it. Is the output leading or lagging the input?
Both.
In the second case,
it is lagging.
In this case, it is lagging. Lagging. And in this case, leading. In this case, leading. Okay. This case, how many say leading? How many say lagging? In this case, how many say leading? How many say lagging? Look at it carefully. This is the previous sample. This is the current sample. This is the current sample of the output. Does this make sense? Current sample of input corresponding current sample of the output. The current sample of the output is behind the current sample of the input. Correct? You are rotating like this and this is behind, right? It's always behind. You are rotating like this. You are rotating like this. And this thing is always slightly behind. It's always slightly behind. So it is lagging. Now this This is the previous sample. This is the current sample. You are rotating like this. And what is happening to the output? Lagging. It's lagging. Slightly behind. Slightly behind with respect to the direction of motion. Correct? Hmm?
Current sample is 1.
Current sample is 1, yes.
And angle is omega, right?
Angle is omega by 2 for the output. Frequency is omega, yes.
But here you consider it as minus.
Frequency is minus omega in this case. Sorry, correct, yes. Sorry. What?
This is corresponding to second.
Second case. This is the diagram for the first case, this is the diagram for the second case. Question? It's lagging for both. Okay?
But here we are rotating it by, like in first case, output was rotated by minus omega by 2. And here it's rotated by omega by 2. In second case.
Yes, in first case the output was rotated by minus omega by 2. In the second case the output is rotated by omega by 2. That's correct. Because the direction of rotation is this way. And so it's lagging with respect to the direction of rotation.
So where is the vector 1 in above case?
This is the vector 1.
So it's leading, right?
No, this is the direction of movement. Am I doing something wrong? Correct, Ada? No. See, previous sample, current sample, next sample, next sample, next sample. Correct? So you are moving like this. Okay? For this sample, your vector is here. Now as you go to the next sample, you are here, that vector is there. Okay? So as you turn, the output vector is lagging. It's slightly behind in the rotation. Slightly behind where you are in the rotation. Okay? Let's come to this situation. Previous sample, current sample. Next sample, next sample, next sample. So you are rotating like this. When you are here, the output is here. When you are here, the output is here. When you are here, the output is here. So the output is always slightly behind where you are in the rotation. And so in both situations, the output is lagging the input. Okay? Okay? Except that if you ask what is the phase angle, in one case you will say that it is, in this case you will say that it's minus omega by 2. In this case you will say it is plus omega by 2. Okay? I think I realize one possible issue that we might be facing. Have you done something like phasor analysis of electrical circuits? Who has had this ever? You have, okay, some people have done this, right? Phasor is a rotating vector. They never show it rotating, so you don't know what's happening. Okay? Right? How come everyone hasn't done it? I thought like, LCR circuits. What? 12th. And okay, so you are not together. So You have gone through like a Fourier transform. Forgotten everything. You are lagging. So, if you have done like, sir, you have all done it. Okay. If you have done this, you gave your JE or something, right? All of you gave your JE or something. No. Not all of us. Is like proudly saying not all of us. What are you talking about? But something like that. And you did this. And there you did this phasor analysis. And that had these I omega kind of things happening in it. Okay. The way they show it in that textbook, they never show you the counterpart. Okay. So the lag for the counterpart spiral has the positive angle is something that you never experience happening in your textbook, which probably has fixed in your mind that lag and the sign of the angle are related. Okay. By the way, that the phasor analysis of electrical circuits, whoever remembers whatever, is just Fourier transform. Okay, they didn't want to confuse you by saying Fourier transform, so they call it phasor, which was no less confusing, but whatever. Okay, again, just so that you know what I keep saying makes sense. You remember you did this for LCR circuits. What is L? Inductor. What is C? Capacitor. What is R? Resistance. Why LCR? Yes. Why not diodes, for example? Was the question.
Gives a negative phase shift. C gives a positive phase shift, and R doesn't shift the phase.
No. Okay. So here's the answer. Why did you analyze LCR circuits using the phasor theory? And whoever remembers it. And the answer to that is that capacitors, inductors, and resistors, the physics of all of these is expressed using linear differential equations. Okay. So their laws have linearity. Furthermore, these are linear differential equations with constant coefficients. You remember this? You had, no? You didn't have it. Okay. Linear differential equations with constant coefficients. Other language. Anyway. So, okay. Linear differential equations with constant coefficients is just a different way of saying linear time invariant systems. Okay? Are you first language, man? Linear and time invariant is something I've been shouting about for 9 lectures now. What is this? Okay. So linear differential equations with constant coefficients is a physicist's way of saying linear shift invariant systems or linear time invariant systems. And phasor is a physicist or electrical engineer's way of saying Fourier transform. Okay. So if you remember this halfly, that's probably because somewhere in your mind, half forgotten, are remnants of the lead and lag phasor theory that you underwent someday, past life. Okay.
Why can't all of them agree to one way of saying things?
If we all agreed to one way of saying and doing things, then we won't have much to do in life.
We can do different things with the same thing.
That's what they claim they are doing. Anyway. Okay. Now, let's say I had a sinusoidal of a frequency omega. What does that mean? A sine wave of frequency omega. What is it? Basically, so this will be 1, this will be what? Sine omega, this will be sine 2 omega, this will be sine 3 omega, correct? That's a sine wave of frequency omega, isn't it? Not, yeah, minus sine omega, but sine minus omega, sine minus 2 omega, and so forth. Agreed? That's a sine wave, correct? Right? Sorry, I drew a cos wave, sorry. Once again.
It won't be 1 then. It will be 1 sine 0.
That's what's wrong. Okay, let's draw a cos wave. Once again. Because it's easy to start from 1. Sorry. Nice catch. Let's a sinusoidal. Okay. Let's draw a sinusoidal of frequency omega. But we'll start with 1 because that's just nice and easy to do. And so we'll start with 1 and then go cos omega, cos 2 omega, cos 3 omega, cos minus omega, cos minus 2 omega, cos minus 3 omega, so forth. Okay? Is fine? And then so this looks something like this. Correct? And then we'll go like this, then go back up, go like that, go back up in both the directions. Right? That is your sinusoidal expressed using a cos function. Now, how do you analyze this going through that same convolution? How do you analyze this? How do you analyze this going through the same convolution 1, 1?
And it will remain a sinusoidal with same frequency.
Why?
Because frequency doesn't change.
But this is a different shape. It's a cosinoidal. It's a different shape, right? We proved that for the spiral shape. This is a different shape.
It's sine phase shifted by half a turn or 1/4 of turn.
That still doesn't make it a spiral.
Sum of two spirals.
Yes. Louder.
It's sum of two spirals.
That wasn't louder.
It's sum of two spirals moving in opposite.
Yes. This cos wave is the sum of two spirals moving in opposite directions. What two spirals? Minus omega and omega. Yes. With what amplitudes and what phases?
Amplitude,
amplitude
half
and-
amplitude and 0.
Half amplitude each and 0 phase. Okay? This cos wave is made up of two spirals having amplitude half each and starting at 0 phase. So half and half becomes 1, and then as they go like that, you always get a real number, which is the cos wave. Is that okay? That's okay, right? You understand that, right? As they go around, let's say this goes here, this goes here. What will happen is you will get a sum that is always on the real axis. Remember, real axis is vertical, the way we are drawing it, and is now falling down to 0 Then as they go here, it will go here, then come back, then go here, come back, and so forth. Is this okay? To be very precise, cos omega n, which is what this is for different n, cos omega n equals half angle omega n plus half angle minus omega n, correct? Yes? And you might remember this in the exponential notation, that cos omega n equals half e raised to I omega n plus half e raised to minus I omega n. Yes? Correct? And so, this cos wave can be decomposed into these two, or at least scales of these two. Half scale of these two, correct? That's strange. Okay. And they were like instantly like, no, this is too much. Yes. So that cos wave is the sum of these two. To be precise, it's sum of exactly half of these two. And so what will be the output that will be produced? Question? You can ask a question.
Oh no, he thought it's hyperbolic.
Huh?
No, I confused it.
The right hand side is complex numbers, right?
Yeah. So, na? If you, so this is, this is half, sorry, this is half e raised to I omega n plus half e raised to minus I omega n, which is cos omega n. Half e raised to omega n plus half e raised to minus omega n without the I is the hyperbolic cos. Correct, no? Yes. Okay. So forget hyperbolic cos, it's just what?
The output of that was cos, no. What was the output of that? That one,
This is that 1 plus cos minus omega. Correct? Huh. But now, so do you understand this? Okay. So it's half of this plus half of this. And so what will be the output? By superposition, the output is going to be half of this plus half of this. Right? Correct? And so now let's try to understand these two things. Both of these are spirals. Both of these are spirals which are going around at a frequency of this is at omega, this is at minus omega. But their starting phase angle is not 0. Okay? And so if you add them up, what will they produce? See, one is starting here and going around like this. One is starting here and going around like this. If you add them up, what will they produce?
On the real line.
Yes, they do produce a simple harmonic motion, which is a sinusoidal. Right? What is the amplitude?
For these two,
Twice.
for the 2 cos omega by 2. Okay.
No, for
Cos omega.
2 cos omega by 2.
2 cos omega by 2 will be the amplitude. Very good. How? Cos omega by 2 coming from here, cos omega by 2 coming from here. Yes, 2 cos omega by 2 will be the amplitude. And what will be the starting phase?
Zero.
No.
Omega by 2?
Minus omega by 2.
How is that a combination of these two?
How is cos omega n equal to half angle omega n plus half minus angle omega n? Is that the question?
No. Like how does half angle omega n translate to that convolution?
So this is basically one angle omega n, correct? So half angle omega n is a scale of one angle omega n. It's the halved scale of one angle omega n. So the corresponding output will be half of this output. So it will be, instead of 2 cos omega by 2, it will be cos omega by 2 angle minus omega by 2 plus omega n. Correct?
Y plus omega n?
As n increases. This, when writing it here, I have just written the initial phase. Initial phase and initial amplitude.
How will the output have a phase of minus omega by 2?
Yeah.
Because we are adding a vector, so now
So let's calculate it. What is the output? The output is going to be cos omega by 2 at an angle of minus omega by 2 plus omega n, correct? Yes? Plus there is another spiral that is going to go again cos omega by 2 at an angle of omega by 2 starting phase minus omega n. Why minus omega? Because the direction is reverse. It's a clockwise spiral. Minus omega n. And what is this whole thing? This whole thing is, is 2 cos omega by 2 cos omega by 2 minus omega n. Correct? Okay? So it's a sinusoidal whose amplitude is this, frequency is omega. No, let's use the frequency of omega, okay? So let's use the other one. Sorry. 1 second. Cos, I like this one better. Omega n minus omega by 2. Which one?
Like, how did you compute this?
Where did you get this expression from the above one?
From the above one?
the cos omega n expression.
I just, like I used Euler's relation, Euler's formula to just decompose it into real part, imaginary parts cancelled out, real parts remained. Correct, na? That's how I did it, right?
Use that expression now.
Yeah, that's how I actually did it. But asked in an exam, how will I do it? I'll do it using Euler's formula. Actually, I just used this, you are right, in reverse. Sorry, is this?
angles are just minus of each other.
हाँ.
वहाँ पे you can put it there.
Oh.
Okay, how does this lead to this? First of all, do you agree that these two are two spirals rotating at opposite frequencies? Yes? Second of all, do you agree that they have the same amplitudes, these two spirals? Third, do you agree that they have the opposite phase angles? Okay? Yes? Given all these three things, that they have the opposite frequency, opposite phase angles and same amplitudes, do you agree that these two spirals will always be conjugates of each other? At every sample, they will always stay conjugate of each other. Yes, because they start with conjugate angles or opposite angles and they continue in opposite directions and they have the same amplitude. So, as complex numbers, they are always conjugates of each other. Okay, agreed? If they are always conjugates of each other, what will the addition always be?
To the real part.
Will be a real number. Okay? But what do conjugate spirals produce? There are two UCMs, what will they produce? An SHM. So, it is producing an SHM. Okay? Now, what will be the amplitude of that simple harmonic motion? It will be double the individual amplitudes of those spirals. So, that is where the amplitude comes from. Okay? I reached here. Now, let me calculate this. The sinusoidal, whatever it is, will have a frequency of omega, that much you agree? So, the omega n part should also be clear. Correct? This is the amplitude, that must be clear. The omega n part should be clear, right? What you seem skeptical.
But the phase is still 0, right? There is no phase.
How is there no phase?
Omega n minus omega n.
No, but where is the phase?
Omega by 2 and minus.
This omega by 2 is the space. There is no n in it. This is the phase.
No, but
Should
that-
be
that-
zero.
there is no, I mean,
You've not put. Isn't
This
cos
entire thing is an amplitude
entirely
function.
of omega n minus omega by 2?
Inside cos.
This entire thing is an amplitude, right?
Haan.
With angle 0.
because there is no,
No, this is the amplitude. This is the frequency, this is the phase.
but if all of this is real, so how will there be an angle in the complex? All of it lies on the real axis.
That is what I am actually trying to explain. That's what I am actually trying to explain, that we speak about sinusoidals which are all real and then we talk about phase angles, but where is the angle? That's what I am trying to explain. Okay? Where are angles in the first place? The angles are in the constituent spirals, which show up as phase lag when it becomes a sinusoidal. There is no angle anymore. There is no complex. There never were complex numbers. This is just our way of analyzing things. There never were complex numbers. There are never angles. All of this is our way of analyzing things. What is actually happening is the cos wave increases a bit in amplitude and delays a little bit. That's what actually happening. Okay?
So you're talking about the phase of the real wave, not I think we're getting confused because we're confusing it with the phase of the imaginary.
Yes. So, correct. So, for a real sinusoidal, this is the amplitude, this is the frequency, and this is the phase. By that is the definition. Yes. No, I just made it up right now, so don't have to assume it anymore. Okay? Sorry, I still didn't explain the omega by 2, did I? Just do a simple thing. You know Euler's formula, right? Just put Euler's formula here, put Euler's formula here. This thing will come out. It's as simple as that. Don't have to do anything more difficult than that. The rest of it is for intuition and helps the intuition. So you have one spiral starting here and going around like this, and you have a conjugate spiral starting here and going around like this, correct? Which together add up to give a simple harmonic motion. Now, since the two spirals didn't start at 0 phase, the simple harmonic motion doesn't start at its peak. Okay? It starts a little below the peak. Right? And then it crosses the peak. Which means that the output simple harmonic motion is lagging in time to the input simple harmonic motion. Okay? This whole thing is a very extended example trying to show you how sinusoidals always lead to sinusoidals using convolution. Right? We didn't really use the fact that this is 1-1. It could have been any convolution. And we could have done this analysis. And simple harmonic motion will always give simple harmonic motion with some amplitude and some phase lag or phase lead showing up, depending on what your convolution is. Okay? Now, if I were to analyze, let us say, if I go on increasing omega, what will happen to the amplitude itself of the output?
It will also periodically vary.
That's not really true because you can't increase omega arbitrarily. How much can omega be? Turns per, it's not turns per second, it's turns per sample. So, ideally till 360, okay? Or actually you are taking negative as well. So, you shouldn't take till 360. Correct. So, minus 180 to 180. Correct. So, if you took, so what happens to this as you go to different omegas? Correct? So, as you go from, sorry, as you go from what, minus 180 to 180, right? So, minus half a turn per sample to plus half a turn per sample. This, what will happen to it? So, here you have 0. What is 2 cos 0 by 2? 2. Okay. Here you have 90 degrees, which is 1/4 turn. What is 2 cos 90 degrees by 2? Root 2. Is it root 2? 2 by root 2 is root 2. Yeah, okay. Root 2. Okay. And here you have 180 degrees. What is 2 cos 180 degrees by 2? It is 0. Correct? And so you have this kind of a shape here. Okay. So for the moment, if you disregard the phase and just consider the amplitudes, what is happening to amplitudes of different sinusoidals is expressed by this diagram. Do you understand it? Right? So as the frequency of the sinusoidal goes on increasing, the response of your convolution is lesser and lesser. It is not hard to see if, at least intuitively, what is a spiral of 0 frequency? 1, 1, 1, 1, 1, 1. Correct? What is the output of this? 2, 2, 2, 2, 2, 2. Okay? What is the spiral of half a turn frequency?
1 0 minus 1 0.
There is no 0. It's 1 minus 1, 1 minus 1, 1 minus 1. Okay? What will be the output to that? No. No. 1 and 1, 1 and minus 1 above, what is the output? 0 everywhere. Okay? So as the frequency goes on increasing, so this is 0. As the frequency goes on increasing, the output actually diminishes in size for the same size of input. Okay? So kind of like, so if this was audio, for example, what would this do? If this was audio signals,
Low pass.
nah, it is a low pass filter. Okay? This is a low pass filter, which means what? It is boosting low frequencies and squelching high frequencies. Okay? So, for example, if you started, if I was speaking into this filter, what would come out is Darth Vader speaking, for example. Use the force, Luke. No, that was not Darth Vader. Anyway, whatever. So, you understand? That's a low pass filter. Who uses low pass filters? Physicists use low pass filters for what?
Because high frequencies are always noise.
Because high frequency, physicists sometimes think high frequencies are a distortion. You want to remove the distortion, so they use low pass filters. How do DJs use low pass filters? Or why? Because they want to boost the bass. Why? Because they want this boom, boom, boom kind of effect to their sound, and so they put a low pass filter in their chain. Okay, I explained to you how to create a low pass filter, simple low pass filter. Okay, you do more complicated convolutions, you can get more complicated shapes here. Okay, so this shape in general is called a filter. And in general, by the way, just a convolution is called a filter in signal processing theory. Okay? Question?
Could you explain, like I missed what that shape is?
Oh, that shape is, that's a good point. That shape is, this shape is how the This shape is the output amplitude for various frequencied spirals
For that particular convolution.
for this particular convolution rule. Okay. So many textbooks, by the way, what I am calling convolution rule, they will call it filters or filter kernels. And now you know why. I avoided using the word filter for 9 lectures because I hadn't explained that yet. But now you know why. You had a question?
Why are we ignoring the second part of the?
No, we are not ignoring that. So this is called the amplitude plot, okay, which is also known as the Bode plot, B-O-D-E, Bode plot. And there is another plot called the phase plot, which tells you what is the phase relation between the input spiral and the output spiral. Okay? And the phase plot here will be what? It will just be as you go from minus half to half. What happens? Wait. Let him first. Yes. No, because it's an important point to understand. Yes.
So ideally, the output will be a multiplication, pointwise multiplication of these two plots.
The output amplitudes will be a pointwise multiplication of sub. No.
Where we calculating this term separately and plotting it, and calculating that separately, when we actually have multiplication in the equation. And there is no notion of an angular rotation here.
Phase of
I have a simpler answer.
We are computing this. Okay, that's a good question. We are computing this diagram from the Fourier transform. Sorry, I haven't used the word Fourier transform today. From the amplitude and phase that the spirals suffer. So there are spirals. While constructing this diagram, it's in the analysis world where spirals exist. Okay? And so in that world, you put in a specific spiral, you get a particular amplitude and phase on your output, and that's what we are plotting, the amplitude and the phase.
So we are actually using the second last equation.
Yes. And the last thing is to show you what is the real world effect of that.
So last thing is resultant of both these plots in some sense.
Is resultant of both these plots at conjugate or like opposite frequencies at a time. Real world signals will always occur like this. Okay. Okay?
So these plots won't capture the direction of rotation. So we have to specify that they are at opposite.
No, positive frequency, negative frequency. They are capturing the direction of rotation. Okay? Tell me what this is. It's this, right? Goes from minus 1/4 to 1/4, correct? This is called the phase plot, this is called the amplitude plot or the Bode plot of the filter or of the convolution. Sorry. That's what I drew. It goes from plus 1/4 to minus 1/4. Correct now? That's what you meant, no?
What are we plotting in the y?
The phase angle of the output spiral corresponding to the input spiral.
This is in turns, radians. What?
Turns, because I'm showing the input in turns, so output is also in turns, let us say. I mean, units are units, right?
If you were to plot them from half to 1, it would go back upwards again. If you were to plot the below ones, like we plot from minus half to half. If you were to plot it from minus half to 1, minus 1 to 1, it would go upward again or go downward.
So, just a minute, what are you doing? What minus? There is no point extending the graph for something that I'll talk about later. So, let's not extend the graph. Okay, your turn frequencies just go from minus half to half. There are no other turn frequencies. Minus pi to pi, yes. Minus 180 to 180, yes.
So here at 0 in this plot, in that equation it should be cos 0 minus 0, right?
Yes, here, yes. Yes. What? Was that the controversy for the last 45 minutes? I am ashamed of myself if that was what was confusing.
Oh, yeah.
Was it?
This makes a lot of things clear.
See, that's why brackets are important.
Sorry.
Now I have to replay last 45 minutes in my brain. I have to rewatch the video.
Okay, who knew there are brackets there and who didn't know? Who knew there are brackets? Okay. Okay, now all of it makes clear. Okay. Is there a way to edit it such that the brackets are always there throughout the video? Then we can just delete the half, like the half hour. Okay.
No, but it's still like cos 0 minus 0, cos 0, 1.
Yes.
So why is it 0?
Huh? What?
So that thing is plotted.
Because this is in angles. This is in angles. This is not in values. This is in angles. Huh.
So, what is minus half and half here with respect to that?
Omega.
Yeah. As in half is like half a turn.
Per sample. Yes. Minus half is minus half a turn per sample. Which are actually the exact same thing. Which is why you don't go beyond them.
Okay. That's just the omega and here's the output.
Yes. Correct. And this is the amplitude output and this is the phase output.
So the phase output have what is there in the y-axis?
The phase.
So whatever is inside that bracket cos. Yeah.
This.
Yeah, what are the values?
Minus, sorry, 1/4, 1/4, 0, minus 1/4. Minus omega by 2. Correct. Agreed? No? Okay. Let's quickly go over all of this once again in the hope that it makes sense. What we have done today is not actually all that difficult, okay? We are trying to show ourselves that a sinusoidal of any frequency passing through any convolution will come out to be a sinusoidal of the same frequency, but it could have a different amplitude and it could be leading or lagging in time the original sinusoid. Very simple point that we are trying to make. Okay? And the way to analyze that, or the way to convince ourselves of that, based on our, the development of the theory we have done till this moment, is that you take that sinusoidal, break it up into two spirals. Each of these spirals is known to come out to be a spiral of the same angular frequency, right? But they could have a different amplitude and a different phase. You add them back, you will again get a sinusoidal, but that sinusoidal could be of a different amplitude and could be leading or lagging the original sinusoidal. Okay? Why? Because if the output spirals have a different amplitude, the output sinusoidal will have a different amplitude. If the output spirals have moved in phase like this, then the output sinusoidal will have moved in phase like this. Okay? The existence of amplitude and phase is actually an abstraction in sinusoidals, but is actually true when you're talking about spirals. And so this analysis can precisely be done in spirals, and which is why even though spirals do not exist, we love this analysis so much that we use these spirals and these complex numbers in analyzing convolutions. Okay? The next question, which I thought I was actually going to address today, but now I will be addressing it in the next lecture. The next question is, which was the next question last lecture as well, is this a complete way of analyzing convolutions? Okay? Here's one way to think about it now. One way to think about it now is that we have shown you that we have shown you a way of analyzing sinusoidals using our technique, the Fourier technique, right? And what happens when they pass through convolution. But what if there are signals that are not sinusoidal? You might say signals that are not sinusoidal might be a sum of sinusoidals. But what if there are signals that are not a sum of sinusoidals? Then you don't know, then you will not be able to analyze that kind of a signal using this technique. Does that make sense? Right? And so, to show that the Fourier transform methodology is a complete methodology of analyzing convolutions, what should I be showing?
That all signals are linear combinations of sinusoidals.
Yes, that all signals are linear combinations of sinusoidals. Right? Because then everything I am saying, it's a complete picture of convolution. Then you can just, instead of thinking of the convolution form, you can think of the filter form. They will be equivalent. Because if I know what it does to sinusoidals, I will know everything about it. If anything can be decomposed into sinusoidals. Okay? Now, to do that completely again takes a lot of calculus. So, we will not do the complete form of that theorem. But we will do a version of that theorem the next time to show you that any signal of a particular kind can be decomposed into sinusoidals. Okay, and then I'll indicate why any signal of any kind can be decomposed into sinusoidals informally. So that will be the topic of the next lecture. Thank you.